Should I start? Okay, so let us continue our discussion of bipartite entanglement, right, which we started off yesterday. So let's go back to looking at this particular state which I wrote down yesterday. I'm going to call this beta 00 for some reason, which will become more clear tomorrow when I speak a little bit more about these kind of states. So let's look at this state a little bit more closely, right? So I want to set up some convention here as to what the 0 and 1 state actually mean for me, okay? So I'm going to write down this sigma z operator. So I'm working in a basis where the sigma z operator looks like this, okay? And so the 0 is basically the +1 eigenstate of this operator, and the 1 is the -1 eigenstate of this operator, okay? So this is just to set up this convention, because when we talk about the inequality today, we are assuming a specific set of, we'll show the violation for a specific set of observables and so on. So this is, as we said, the joint state of a pair of quantum systems. And as I explained yesterday and maybe convinced you, that this is a state which cannot be written as some state phi A in subsystem A, tensor product some other state phi B in subsystem B, okay? And this is something, like I said, you can easily check. You actually try to write down a tensor product like this with some arbitrary coefficients, and you will find that some inconsistency in trying to solve for these coefficients. You will find that there is no way to solve for a pair of states like this, right? So this is a state which cannot be decomposed into a tensor product of a local state in A and a local state in B, right? And so we call such states entangled states. And we realize that because I have written this out now in this way, in the sigma z eigenbasis, if in subsystem A, somebody were to make a measurement of the sigma z observable and they get outcome +1, then the same outcome should occur in subsystem B as well. Similarly, if the outcome -1 was obtained, then the same outcome. So this is what one means by correlations, right? So this, in this state, the sigma z outcomes are perfectly correlated. And this is what we think of as a signature of quantum entanglement, right? That when one makes a measurement in one subsystem, that somehow tells you something about the state in the other subsystem. And I hope everyone sees, at least mathematically, why this is happening. If I were to think of putting this Stern-Gerlach measurement box like we did yesterday and so on, you'll realize that there is a collapse happening in subsystem A, which means that this superposition here between these two states must be broken, right? And that is what tells you that therefore the outcome in subsystem B must also be the same, which is +1. Yeah.
What's the difference between this correlation and entanglement?
So the outcomes of a measurement are classical. When I make a general measurement, so in this case, it's a two-valued measurement, right? It's +1 or -1. So the outcome I can think of as essentially a binary valued classical random variable. And the outcome in subsystem A is one classical random variable. The outcome in subsystem B is another classical random variable. And because the joint state is in an entangled state, these two classical random variables, which you get by making measurement, are correlated. So the outcomes are classical random variables which are correlated. The state is entangled. That's the semantic difference that one's talking about. But yesterday I also then asked this question, okay, I cannot represent the local states as pure states, but how do I then, is there a way to talk about the local states for this kind of an entangled state? Okay, and I want to briefly talk about that before I move on to the Bell CHSH inequalities. So I want to talk about the local description. Which basically leads us to talking about something called the reduced density matrix. I mentioned this, I think, towards the end yesterday, but I just want to dwell a little bit on that. So the way to get to this reduced density matrix is to consider, consider this joint state, right? If I were to write this as a density matrix, this is what it would look like, right? This is my joint density matrix. In this case, the joint state is a pure state. I could have a situation where the joint state is truly a mixed state, right? But in this case, associated with this particular bipartite state, this is the density matrix. It's simply the projection onto this state, right? Now, what is the reduced density matrix? It is very easy to define. It is simply the partial trace of this joint state. If I want to know what is the state on subsystem A, I trace out over B and I get this reduced density matrix here. And if I want to know what is the state in subsystem B, then I trace out over A and I get this. And I assume that people here know the idea of a partial trace, right? If you want to expand it in a basis and C, then basically what you're doing in some sense, so a very loose way of writing this would be, I have some basis in B, so these are two-dimensional systems, so let me say I pick the 0, 1 basis itself, then essentially this is doing something like this. Okay? Remember, this is a state of C2 tensor C2. I'm taking these, not exactly, I'm acting it on a ket vector which is only on a single C2 system. On this side, it's acting on a bra vector on a single C2 system. So what I should be left with is an operator on a single C2 system, and that is this reduced density operator. Yeah.
I'm sorry, on the left you have an operator, and on the right you have...
That's exactly what I was trying to say. So this is a joint. This is an operator. This is a four-dimensional. This is a 4x4 matrix. These are two-dimensional vectors. Okay. So maybe it is useful to just do this computation once. So let me write this state out in all its gory detail. So this is basically a state that looks like this, right? So this is 0, 0 plus 0, 0, 1, 1 plus, oops. And when I take the partial trace over B of this, then I have to sandwich on both sides with the ket 0 in B and the ket 1 in B, and you realize that these cross terms are going to go away when I do the partial trace. So what am I going to be left with? I'm going to be left with the 0, 0 in A and the 1, 1 in A. Is this clear? So this is how you do the partial trace. This case, I'm doing it with an example. You can think of doing this for arbitrary dimensions and so on. But the nice thing is we now have the reduced density matrix in A. And what is this reduced density operator? This is identity. So this is the identity operator in A normalized to make it a density operator. Similarly, you can work out that the reduced density matrix in B will also be the identity operator in B normalized to make it a density operator. And remember, we called these maximally mixed states yesterday. Which means these are the states with the largest entropy in each subsystem. In this case, it's log 2, which is 1, right? So these are the subsystem density matrices are states with the largest entropy. So if I were to just think of this, somebody prepares this state, let's say, in a lab, pair of entangled photons, distributes it to 2 neighboring labs which are spatially separated. The person who made this joint state tells them that they are in this kind of a perfectly correlated state. Nonetheless, the only information that each party has who holds this single one half of this entangled pair is this reduced density matrix. So, yeah?
Is there a way to reconstruct the joint density matrix from two marginal ones?
So what do you think in this case?
I think no.
You think not, exactly. So that's exactly the point, right? Because if I now think about this information theoretically, how much information do I have in the joint state? So what I'm asking is, what is the entropy? Looks like I need more boards. Huh? Okay, so let me erase this part. What is the entropy of the joint state? What kind of state is the joint state? Pure, mixed? Pure. So what should its entropy be? But we just saw that the entropy of these reduced states, because they are in the maximally mixed state, is log 2, which is 1. So this is one of the key signatures of quantum entanglement, that there is more information in the whole than in the marginals. So my advisor used to like to talk about this as the entire book containing more information than the sum of its parts. So you cannot hope to take this book apart into parts and put it back together, because the local knowledge that you have from each part is actually very less. You have maximally uncertain states which lead to maximum uncertainty as the local states. But the whole is actually a pure state about which you have perfect knowledge, right? So the entropy of the whole is 0, but the entropy of the parts is maximal. Okay, and this is one of the signatures of being in an entangled state. And I should also mention that this is something which is somewhat counterintuitive if you were to think about classical entropies and classical random variables, because the rest of this lecture is also going to be about how are these quantum correlations different from classical correlations. Why is quantum entanglement different or special, right? Can you not have these kind of correlations in classical random variables? Now, in the classical setting, remember I distinguished the classical entropy as H. So I can think of 2 different random variables, one represented by A, another represented by B, and I can write down a joint entropy of this pair of random variables. Okay? Classically, I can ask, how is this related to these individual entropies, right? And you can show classically that this should always be less than or equal to the joint entropy. Which kind of makes sense. Your extent of uncertainty about each individual random variable cannot be greater than your degree of uncertainty about the joint, right? But these kind of entangled states kind of spectacularly violate this notion, right? So this is classical. Another way to sort of think about this, very briefly I want to talk about so you can ask in the classical case, I have this I have a pair of random variables, right? And there is some joint distribution over this pair of random variables. Suppose I have knowledge about one of them. How much uncertainty do I have about the other? Right? So in probability sense, you're saying given that a particular event occurred, what is the probability of some other event happening, right? In this joint case. That's what you would call a conditional probability, and this was mentioned in the previous lecture also. So, and you can take this idea to entropies and talk about a conditional entropy. So you can talk about what is the conditional entropy of A given B. And your intuition should tell you that you have this joint distribution, you have a pair of random variables, but now you have complete information about one of them. So in a sense, you have removed the uncertainty about one of these, right? And so there's a very intuitive formula which works, which is that it should be this joint entropy with the amount of uncertainty that you would associate with the B random variable alone taken out of this joint entropy, right? I'm not proving any of this, I'm just sort of waving my hands around and so on because we don't have time, but it's very interesting. So this quantity is a nice positive quantity in the case of the Shannon entropy and classical random variables. But now you can try to write down something similar in the quantum case. Can you write down a conditional entropy in the quantum case? And you realize that because you have these peculiar states where the individual subsystem entropies are actually larger than the joint entropies, if I tried to use an analogous definition for, so quantum conditional entropy is often written like this with the conditioning here when you put the labels of on the system, right? If I were to define it the same way as S rho AB minus, in this case, sorry, S rho B, you can see that this is actually less than 0 for this entangled state. So let me not, I have not proven any general statements here. I'm just showing you some examples. So this is for this state. So in the early days of quantum information, this was realized and people were sort of stunned that there could be this idea of negative conditional entropy, right? And there are some very nice papers written during the time that people discovered this. And today we understand this more. There are some operational meanings for what this negative conditional entropy means and so on. Can it be used as a resource and so on and so forth. But this is just to show you that in contrast to classical intuition, this sort of thing can happen. Yeah. So this is, okay, so this is saying that you have some knowledge of subsystem B, right? So that's a good question. So how do I actually even write down this kind of a state, okay? That in itself is an interesting question in quantum information. We will not go into that, but just think of this as, yeah, so no, I have some knowledge of subsystem B, then conditioned on that, what is the entropy in A, or what is my uncertainty about A, right? In an analogous way that we ask the question for classical random variables, okay? Imagine that you have a state in A conditioned on some knowledge of B. Okay, I have a joint system, right? And, okay, for now maybe just think of this as this quantity, right? So these are well-defined notions. You have a notion of joint state, which is here. You have a notion of the reduced state. Okay? So just think of it as the difference between these two entropies. Okay? And if analogous to the classical case, I want to call this a conditional entropy, then I will violate this principle that my entropy should be positive. I will end up with negative values. Okay? So,
Yeah, I want to ask a question here.
yeah.
I understand actually this entropy of rho AB being 0, but typically we say that the entropy is also information, right?
Yeah.
I'm unable to sort of reconcile this idea that the full state has the highest information, but there is entropy which is telling me that it's 0. What does it mean? I mean, it's a bit confusing to me.
Zero entropy is the least uncertain state.
Yeah, that
right?
makes sense.
So lesser the entropy, right? More certain you are about the state, more knowledge, more information you have about the state.
But typically we interchangeably use the information being the entropy.
So they are complementary notions. No? When uncertainty is high, you have lesser information. When uncertainty is more, you have, so it's just, I think it's just the semantics of it that you're confused about. So maybe think purely in terms of uncertainty, if that is more comfortable. Just say that this is a state which has zero entropy, which means I'm maximally certain about this. There is no uncertainty about this state, right? Whereas states like this are states of non-zero entropy, and you have some uncertainty about the state. So,
Can we think of it as like strings of letters? For example, like, you know, in the previous lecture, professor was telling us about entropy being as like how many binary questions can you ask, or should you ask, right?
Yeah.
That will be the number. So when you
so
say S is
that,
0,
that way of thinking about it, I would say is like asking how much information am I actually uncovering when I make a measurement of this state? Before I made the measurement, I was uncertain about this by this amount. So when I make a measurement, I am learning these many bits of information. Does that make sense? So that is the sense in which I'm saying that they are complementary notions. Without measurement, without asking these questions, this is how much uncertain I am about the state. And this is conversely how much information I will uncover in bits when I learn this state. So that's, yeah, hope that clarifies.
In quantum entropy, so our whole system has lesser entropy, that means we have more information, but our subpart has less entropy, so greater entropy, so that means we have less information.
Yes.
But when we go to classical case, it is inverse. So when we have the entropy of the whole system is less greater than the entropy of some system.
Yeah, for classical random variables, this is always true that the joint entropy will always be greater than the individual entropies.
Isn't it counterintuitive that if we have our full system, then we have less information, and in classical case, since entropy of the full system is greater, so the information in full system is less, but in
Okay. So as I was just explaining, when I say that the entropy is greater, I mean that your degree of uncertainty about that is greater. And the amount of information that you can learn by learning that is greater. Okay? Don't think of it as information. Think of it as certainty versus uncertainty. Okay? Or think of it as how much information how much information is contained in something. Okay? So let's maybe just stick to certainty and uncertainty. Maybe that will make things better. So I'm saying that if I have this joint random variable AB, then I cannot be more uncertain about the individual ones than about the joint. My uncertainty about the joint is greater than my uncertainty about the individual ones. Okay? Whereas in the quantum case, it's possible that my uncertainty about the joint is actually lesser than my uncertainty about the individual parts. Okay?
Is it due to the fact that if we know the state of A, we can easily guess what is the state of B in this entangled state?
So the correlation part comes in later. So what you're saying is, if I measure A and I know A, then I know what outcome I should get in B. That is true, right? But this is, no, this is saying something more, right? This is saying that your knowledge of the local parts, your knowledge of the local states is much lesser. Your uncertainty about the local states is much larger than your uncertainty about the whole state itself, right? When I say that I know what the outcome in B is given the outcome in A, that is presupposing the knowledge of this joint state. Like I said, I make this joint state and I send it across to two people and I tell them that I have sent you this entangled state, right? Then, and only then, when A makes a measurement, can he or she predict the outcome of B. Without knowledge of that joint state, you are not able to predict. But the point is, even with knowledge of the joint state, locally, when A first makes the measurement, he or she doesn't know what they're going to get. 0 and 1 are equally likely as far as the local subsystems are concerned. Even though they have complete knowledge about the joint state, their local states, they are completely uncertain about it, right? And so the point I want to come to is, suppose A makes the measurement and A does not tell B the outcome of her measurement. Okay, you are in two separate labs, A and B are in two separate labs, A makes a measurement. A does not pick up the telephone or yell across the corridor and tell B what outcome she got. Then, what is B's state of knowledge or uncertainty about it? It is maximal. The uncertainty is maximal in B. Without knowing the outcome of A's measurement, the only knowledge that B has about the state is this. So as far as B is concerned, it is still a coin toss, whether B is going to get 0 or 1. Okay? And so I'm starting off by already telling you, in a sense, that there is no paradox. Although next I'm going to tell you about the EPR paradox and so on. I have this bipartite entangled state where there are correlations, and a measurement on one subsystem definitely forces a certain outcome on the other subsystem. But whether the other subsystem actually has knowledge of that outcome, right? Information theoretically speaking, subsystem B, until and unless the measurement outcome of A has been communicated to B, does not know what outcome to expect. Both outcomes are equally likely in this case. Okay? So the local, this idea of the, what is the local state of knowledge of these systems is an important thing to keep in mind when one is talking about entanglement and non-local correlations and things like that. Okay? So maybe I'll move on to talking about Bell CHSH, although there were a few more things I wanted to say here, but maybe in subsequent lectures we will do that.
I'm sorry, what do you mean in this case by communicated the results of...
Yeah, so there is a classical random variable that A realizes by making the measurement, and the value of that classical random variable has to be communicated to B for B to know that he is definitely going to get the outcome 0. If that classical random variable has not been communicated to B, all that B knows is he has this reduced state and he is going to get outcome 0 or 1 with equal probability.
But I just don't understand what the communicated part means in this thing. For example, if like A makes a lot of measurements and like gets 0, 0, 0, then B will get 0, 0, 0 as well. But
absolutely,
when
yeah.
no communication, what do you mean?
So
It will be like...
the correlations are non-local, okay? But in a causal sense, there is no violation of causality in the fact that there exist these non-local correlations. Because it is not as if the existence of these non-local correlations gives B predictive power, right? It only forces the outcome in B to be something. But for all B knows, I could have just cheated, right? I could have kept sending a random photon which is always in the plus Z state, okay? And so B always gets 0. What is to say that I actually sent them an entangled state? So unless they talk classically, yeah, and then they are limited by speed of light, etc., etc. So today in quantum foundations and quantum information, people talk about a notion of information causality, right? That you do not have flow of information faster than light. This is sometimes called the no signaling principle and so on, right? And what one is saying here is, yes, there is non-locality, but the spookiness aspect is somewhat taken away when you realize that unless there is this classical information being communicated, it is not like B has superpowers or A has superpowers because they have an entangled state, okay? Okay, so the reason I also wanted to talk about the reduced density matrix is to talk about the subsystem von Neumann entropy and the Schmidt, in the Schmidt contest. So let me quickly also talk about that. So remember we said that last evening that every bipartite state can be written in this so-called Schmidt form, okay? So there always exist these local bases such that you can write down any bipartite state in this form. In this form, what is now the reduced state in A and B? So the joint state is now of this form. So let me write, okay. So let me just do 2 steps of this calculation maybe. Again, it's a generalization of what I wrote there, but maybe it's okay to write this. I'm going to write K comma L going from 1 to R. Let's say I have lambda K, lambda L. Oops. So I have this, I have all possible cross terms like there, but you realize that all those cross terms go away when I do the partial trace. Now I'm going to pick the Schmidt basis to do the partial trace, right? Obviously, it makes sense to now do the partial trace in this basis. So if I now do this same partial trace like what I did there in that example, in this Schmidt basis, then I hope you see that the reduced states look like this. So the key thing to realize is this set of eigenvalues of these 2 reduced. So these 2 reduced density matrices are diagonal in these 2 bases. So these bases are called the Schmidt bases. Okay? And the Schmidt basis, so the reduced density states are diagonal in the Schmidt basis, with the eigenvalues being simply the square of the Schmidt coefficients. So when I write down the subsystem entropy, the von Neumann entropy of these reduced states, which is what I call the subsystem von Neumann entropy, you realize that they both have the same subsystem entropy. So you realize that S of rho A is the same as S of rho B, which is minus sum over K, lambda K squared, log lambda K squared, and this is what we call the subsystem von Neumann entropy. It's one of the simplest measures of entanglement that one can think about, although if you have very large systems like many body systems and so on, it's not the easiest to calculate because you need to get to these reduced density matrices and then diagonalize them to get this entropy. But it is a very nice measure of entanglement, right? Why is it a measure of entanglement? Because suppose my subsystem states were pure states, right? If the reduced states were actually pure states, when is that possible? There's only one non-zero lambda k. So there's only one term in the Schmidt expansion, right? Which means my joint state was basically a product state. So when this is 0, this is often called, I think, SVNE, right? So let me just use that. So I'm just going to say that if this is 0, it implies that the joint state is a product state, is unentangled. Any value of this greater than 0 means that the joint state is entangled. And now you can ask what is the maximum value that this can take. So like I said, if this was dimension D1 and this was dimension D2, then you're constrained by the dimension of the smaller system, right? So the maximum that this can be is basically log R, right? Because this is now a probability distribution over R discrete outcomes, right? So this is log R. Remember yesterday we called R the Schmidt rank of the state. So R is the number of non-zero Schmidt coefficients. This is called the Schmidt rank. And when your subsystem von Neumann entropy is indeed equal to log R, that is when you would say that the state is maximally entangled. So this is the case when the joint state is maximally entangled. Yeah.
Sorry, do I understand correctly that no matter what the nature of the joint state is, the entropies of subsystems are always equal?
Yes, yes. So indeed, if I have a pure bipartite state, so let me state this theorem. It is indeed one of the so-called properties of the von Neumann entropy, that if you have a pure bipartite state, then S of rho A is always equal to S of rho B. So that is the sort of power that doing the Schmidt decomposition gives you, right? So, okay. So the minimal value is 0 for product state, maximum value is log R, which tells you that the state is then maximally entangled. So in the case of the two-dimensional system, we have indeed written down such a maximally entangled state, which was one of the Bell states that we just discussed, right? Yeah.
Greater than inequality should be in entanglement statistic. So means if my entropy is greater than 0 but less than log R, then it is entangled.
It is entangled, but not maximally entangled.
Yeah, so for the last case, it will be just equal to log R, isn't it?
So I'm sorry, I want to say equality. Yeah, sorry. I wanted to say that this is an upper bound. You're right. Thank you. So equality. Okay. So I wanted to say that this is a lower bound and this is an upper bound, and lower bound is for product state and the upper bound is for maximally entangled state. Yeah. And notice that the fact that the joint state is maximally entangled is exactly corresponding to the reduced state being maximally mixed, right? So the reason you're getting this maximum entropy here obviously means that then all of these lambda k squared are just 1 over r, right? And so this is a maximally mixed state in each subsystem, and this again is a signature of maximal entanglement, right? That the joint state is pure, zero entropy, the reduced states are maximally mixed, okay? Okay, so now this gives you some machinery to analyze entanglement in bipartite pure states. So let me now change tracks a little bit to talk about this notion of non-local correlations and what is really unique about the quantum case. And the machinery we'll use for that is basically the idea of Bell CHSH inequalities. So I hope I can erase this part now. So there's a little bit of history to this, and maybe it's good to also pause here and say a few things about the history of this question. So the idea that there exist entangled states in quantum mechanics is something that the early founders of the theory realized very soon. Whether it was Schrödinger or Einstein, they knew that these kind of states existed. Interestingly, it didn't seem to bother Schrödinger as much as it bothered Einstein, for whom this seemed to suggest a certain incompleteness in the theory itself. And the argument that they made was as follows. So the story starts with the famous EPR paradox paper, 1935. And as we heard the previous lecturer say, whenever you say there's a paradox, it means you do not probably understand something very well, right? So the paradox that they came up with was this idea that, so EPR in their paper, they thought about a state which is similar to the Bell state that we wrote down, except it is now entangled in position and also momentum. So they thought basically about a pair of electrons which were somehow initially in an entangled state, and then you take them apart, and now if you measure one of them, the position of one of them, you know the position of the other. If you measure the momentum of one of these particles, you know the momentum of the other because of conservation laws and so on. Now, it was already realized that position and momentum being non-commuting observables, they are complementary aspects, so to speak, of a physical system. We saw this with the Stern-Gerlach setup the other day. You cannot simultaneously have information about complementary aspects of a system, so you cannot simultaneously have information about position and momentum. So the way they phrased it is in terms of what they called aspects of reality. So the question was, position and momentum we know cannot be simultaneous aspects of reality of a physical system, but now if you have this entangled state, you make a measurement of position here, you know something about the position there, you make a measurement of momentum here, you know something about momentum there. So it's as if without making a measurement on the second subsystem, even before making a measurement, position and momentum are both, one is able to assign values without making a measurement on the second system, right? It's a thought experiment, but it seemed as if this was now counter to the understanding that these were complementary observables, and so you could not simultaneously assign values to them, right? Very loose description of what it is, but this was the sort of apparent paradox that they came up with. Subsequently, David Bohm rephrased this for spin observables like the sigma x, sigma z that we spoke about. And maybe it's worth writing down so I think this is sometime in the 1950s. So the kind of state that Bohm looked at is a different beta state. I think this is, so I'm going to call this something else. Let me say beta 1, 0 or something. And this was the state that he looked at, which was 0, 0 minus 1, 1 by root 2. Same sigma z basis, you can think about this, right? The same setup. This is your spin singlet state actually, right? I mean, yesterday I wrote down the triplet and I called it the singlet. I'm sorry about that, but this is your singlet state. Now the interesting thing you observe about this state is, I'm writing this down in the eigenbasis of sigma z. What happens if you write it in the eigenbasis of sigma x? Can you do this computation for me, maybe? Basically, you know that 0 is, so remember that sigma x eigenstates, I have this notation where sigma x eigenstates are written as plus minus, which is 0 plus minus 1 by root 2, equal superposition, but one of them with a pi phase, right? So conversely, you can rewrite your 0 and 1 in terms of plus and minus. You do that, you realize that this state looks like this. So the exact same correlations get carried over to the, oh I'm sorry, did I want to write 0, 1, 1, 0, I'm sorry. Yeah, I'm sorry, I wanted to write down the perfectly anti-correlated state, I'm sorry. Okay, so please fix this, huh? Sorry. Yeah. Okay, so anyway, this is something for you to check. So now the point was that you have these two, this, let's say, pair of electrons, photons, whatever, and you're making these measurements first in the Z basis. Okay, see now there's another aspect that is brought in here. So far we were just looking at an entangled state and we were saying, okay, there exist correlations if you make measurements of a particular observable. Now I'm saying you're not making measurement of a single observable, you're making measurements of two different observables. Okay, and in particular, these are complementary observables. These are observables that satisfy an uncertainty relation, sigma x and sigma z. But you realize that the same anti-correlation in this case exists also in the sigma x basis. The same anti-correlation that exists in the sigma z basis also exists in the sigma x basis. So now the game gets more interesting. A has the option of making measurement either in sigma x or in sigma z. B has the option of making a measurement either in sigma x or in sigma z. Okay? And then the same kind of paradox arises that is it then possible to assign values to x and z and therefore in a sense making them both simultaneous aspects of reality for the quantum state, which otherwise quantum mechanics prohibits. Okay, so this was Bohm's version of the same paradox, and then of course this was, so the sort of idea that whether Einstein or Bohm had was that there must exist some missing variables in the theory. This state that one is writing down, whether it's this beta 1 0 or beta 0 0 or whatever that I wrote down, this is not a complete description of this joint state. There are what they called hidden variables. So maybe there is some underlying random variable, and some density over which it is distributed, which if you have knowledge of, you can actually write down all the probabilities that you want, and then you won't have this paradox. Okay? So this is what today people talk about as hidden variable theories and so on. So this was all still somewhat of a philosophical discussion until Bell came along in '64 and formulated a very precise way of testing this, right? So the question is, if I have what I think of as, okay, so let me write down the precise formulation that Bell and then later on CHSH came up with. If I believe that my physical theory has to be local and should have well-defined what I call elements of reality, then what kind of correlations can exist in this kind of a bipartite setting? So let me now get down to the brass tacks. So this formulation that I'm writing down is a combination essentially of Bell's work in 1964, and I think the CHSH paper is, I don't have the precise year for that, it's sometime in the 70s, okay? So this is the sort of formulation that they came up with to make this question not a philosophical one, but a somewhat concrete, testable one, okay? So we start by saying, okay, consider a general probabilistic theory, okay? I'm not saying now whether this is classical mechanics or quantum mechanics or whatever it is, just consider a general probabilistic theory where I have two systems which are space-like separated, okay? And let's say that they share a joint state. Yeah, this is the setting in which all these paradoxes are phrased, okay? Now let's say that, what do I mean by saying that this is a probabilistic theory? So I think of observables in this theory as random variables which can take one of two values, okay? So I write down some set of observables for each system, each of which can take, in this case, binary valued random variables plus minus 1, okay? Now, I make some assumptions for this theory to be what I think of as a reasonable physical theory, okay? So the assumptions I make are, firstly, this whole idea of realism. So I'll state this and then I will maybe say in words what I mean by this. So these four observables that I wrote down, these four measurable quantities, they are objective properties of the system. So this kind of idea is, maybe today you think of this as a classical intuition, but it is what you might reasonably expect. If I talk about the dimensions of my tablet, I don't expect the outcome or the value of this dimension to depend on whether or not this was observed. I don't expect the act of observing the system to change the values of these observables. So these observables basically have values in an objective fashion, independent of whether or not one has measured, one has looked into it, and so on, right? So all four observables, if they are such elements of reality of the system, then it should be possible to assign values to all four of them, irrespective of whether one has measured something or not measured something and so on. So that is what one means by objective elements of reality, okay? And the second, of course, is locality, which also we believe that physical theories should be. So the subsystems A and B are basically causally disconnected. So A and B are outside each other's light cones, so they are, say, causally disconnected. So basically one is assuming this physical theory to be a local realistic theory. Note that one is not saying anything about hidden variables, etc. So there could be hidden variables, whatever it is, but the ultimate theory is a local realistic theory. Okay? So in a sense, one example theory that you can think of for this is quantum mechanics with hidden variables. Okay? So the kind of question that Bell was basically asking is, if you allow for quantum mechanics with hidden variables, where you impose this local realism constraint, which kind of normally holds true in our classical worldview, right? Then do you still get the kind of correlations that you see with an entangled state? Do you still see this sort of paradoxical situation or deviation from classical? Yeah. Exactly, some other random variable that you don't know about, that your experiments have not yet accessed. Okay? And then if you have these hidden variables, you can again ask, are these hidden variables local or non-local? Meaning, is it a joint distribution over A and B, which then survives this space-like separation between them or not? Are they realistic, etc., etc. So anyway, so let's now look at this, and then the CHSH inequality is now very easy to state. The form in which Bell stated it is somewhat different, but the simplest way to state this is the form of CHSH. By the way, I hope everyone knows CHSH is Clauser, Hone, Shimony, and Holt, of which Clauser, of course, was one of the three awardees of the 2022 Nobel Prize. Okay, so what is the CHSH inequality? It says the following. So now we consider a pair of observables here, a pair of observables here, and we write down an observable M, which is a function of these four observables, which is of this form. So it is PR plus QR minus PS plus QS, okay? And then all of these take values plus minus 1, right? Exactly binary value, discrete valued observables, taking values plus minus 1, right? And so you realize that if P, Q, RS are of this form, then M itself can only take values plus or minus 2, okay? Sorry? M. It's another observable which you're constructing as a function of these observables. So you can think of some, I don't know, it could be position, momentum in one case, and you're taking some function of these different position momentum functions, for example. We'll write down some concrete example because we are going to show that this classical intuition gets violated when we write down certain states. So now the,
I'm sorry, is it
yeah.
that there is a minus 1 before 1?
Yes, yeah. So this set of, this function has been sort of carefully constructed to see a violation, right? And in the end, I'm going to tell you that there is something optimal about this construction, but yeah, just say that someone gave you this function of these four observables, okay? Now you can, so I said this is a probabilistic setting, right? So these, there's some probability with which each observable is taking these values, okay? I'm not going to write down all the details, but I'm just going to say you can think about the expectation value of this observable M, okay? So I'll call this E of M, and you realize that because you're constrained like this, your E of M must essentially be less than or equal to 2, right? And that's it. This is the so-called CHSH inequality. Okay? So by Now, what has gone into this? For you to be able to write down this expectation value, you need to have had a joint probability distribution over P, Q, R, and S. Okay? This becomes a crucial ingredient in writing down this inequality, right? And you have the ability to simultaneously assign values and the fact that they are causally disconnected simply tells me that anything that's happening here is completely independent of anything that's happening there. So I'm not going to write that down separately, but this is the sort of hidden assumptions that are going into getting this inequality. So then what do CHSH do? They say that, okay, if I assume a local realistic theory of this form, this is what I expect such a function to have. However, I'm now going to show you that there exists in quantum mechanics a joint state of a pair of causally disconnected systems and a set of observables for which this is going to be violated. Okay? So of course, the joint state is going to be one of these maximally entangled states. So it is indeed, so you can consider this fully antisymmetric state that I wrote down, right? I'm sorry, I'm changing notation. So I think I called this I wrote down a different state earlier, so I'm going to label this slightly differently now. So this is the state that I call beta 1, 1 actually. I mean, this will become clear tomorrow when I show you how these states can be prepared. So this is the same state that I wrote down short while ago, and I said that the state carries through the same anti-correlations in other bases as well, right? And these are, like I said, eigenstates of Z and so on. So now what are these observables? So here is the set of 4 observables. So let's say P is sigma Z, Q is sigma X, R is minus sigma Z minus sigma X by root 2, and S is sigma Z minus sigma X by root 2. So I'm going to leave this as an exercise to you to show that if you now compute this expectation value for this set of 4 observables, now what do I mean by PR in this case? So I have to be a bit more careful, right? So let me maybe write down one term here as an example. So in quantum mechanics now, what is expectation of PR? P is an observable in subsystem A, R is an observable in subsystem B, right? So what I mean is actually this expectation value in the state which I'm calling beta 1, 1 of essentially P tensor R. So this is sigma Z tensor, whatever this is, minus sigma Z minus sigma X by root 2. So this is an observable acting on the first. So when I write down this tensor product, I have a sequencing in mind here. This is A and this is subsystem B, just like how here this is A and B and so on. So it's a little bit of jugglery of bracket notation, right, which I will leave you to do. It turns out that this value is just 1 over root 2, okay? And it will turn out that you get the same for all 4 terms with the minus sign for the term with the minus sign. And so it will turn out that, I have to write this somewhere now. Maybe I will just write this here. So in quantum mechanics, this expectation of m in the state beta 1, 1 turns out to be actually 4 over root 2. So this becomes 2 root 2, which is of course greater than 2. And so you have in quantum mechanics a violation of this simple inequality, which you think should hold true for any theory, right? Because you made reasonable assumptions. But it turns out that some of these assumptions, like I said here, turn out to be not so reasonable in the case of quantum theory. So is the setup and the idea clear? And then we'll discuss, we have some time to discuss. Yeah. Yeah, exactly. Yeah. Okay, so the math is not very difficult, right? Except you have to do some linear algebra, I mean this bracket and algebra here, but otherwise it's very simple, right? Very simple to see this 2 root 2. Yeah.
There will always be only 4 parameters, P, Q, R, and S.
So this is today what you think of as one example of a Bell setting, okay? You have a pair of dichotomic observables. Dichotomic means 2 outcome observables. So there are some choices here, right? So A has a choice of measuring P or Q. B has a choice of measuring R or S. And each observable has 2 outcomes. And there are 2 parties. So this is what is today called a 2-2-2 Bell type scenario. You can now generalize this. So with whatever fancy set of numbers you want. You can think of a tripartite setting, which in fact the 3rd Nobel laureate of 2022, Zeilinger, he has his name associated with a tripartite quantum state called the GHZ state, and they came up with a version of this where you add a 3rd party to the mix, you extend this kind of Bell-like state to 3 parties, and you can formulate a similar inequality, right? You can extend each observable to be now of higher dimensions. You can consider multiple observables here, and you can ask what is the bound, etc., etc. Yeah.
I'm sorry, where in the classical scenario an existence of some hidden variables can be assumed?
So I'm saying that's why I don't think of this, I did not say that this is classical theory. I said think of this as a general probabilistic theory, which could potentially have hidden variables, okay? But even those hidden variables have to satisfy these assumptions. That's the crucial thing. So after Bell's paper and CHSH paper and even the experimental violation, today what quantum foundations people will tell you is what this has shown is that quantum mechanics is not consistent with a local realistic hidden variable theory. But it does not, for example, exclude a non-local hidden variable theory, because I'm still making this assumption here. I could construct a general probabilistic theory which admits, for example, non-local hidden variables and ask now what is the inequality, what is the bound that I get. Okay, so this setup excludes, or it says that quantum mechanics is not consistent with a local realistic theory, whether it be apparent or hidden, but it is not consistent with a local realistic theory. Yeah.
So we had 4 hidden variables, P, Q, R, and S.
No, these are observables. They are not, I'm sorry, they're not hidden variables. Maybe I shouldn't have mentioned, I just wanted to, they are just observables. P, Q, R, S are observables. Yeah.
Construct another observable consistent.
Which is a function of these 4. Yeah. Yeah. Yeah.
And we are saying that it should expectation of value of this variable should satisfy.
We put a bound on this. Yeah. Yeah.
So first question is why we put a bound on this, means how this bound is coming to this expectation value of this.
So I make them binary valued So you can think of it like this, right? So what is the expectation value of P itself, right? Let's say that there is some probability of 0 times, probability of plus 1, right, times plus 1 plus probability of minus 1 times minus 1, right? Similarly, you write down probability now of the joint PR, right for QR, right for PS, right for QS, and then sum it all up. So, and then you basically, because these observables can take only plus minus 1 values, and you know that these are probabilities, you can put a bound on this, right? That's all. So, in calculating this, you actually write down, so maybe I will just, so the way you would formally write this is to say, let's say there is a joint distribution of this form. Yeah, so let me call this some big probability. So let's say little pi is the outcome of this measurement. In this case, it's only binary. Little qj is the outcome of this measurement. Little rk is the outcome of this, or let me not say even measurement. Let me just say that that is the value that this observable takes, right? Those are the little letters. And then there is a joint probability distribution over this set of 4 random variables, binary valued random variables. So I take this joint distribution and I take this function and I sum it up to get the expectation value. It's just to say that little pi can be plus 1 or minus 1. Yeah. Yeah, that's all.
Also, why this form of M is special? We could have, so there must be something special about this.
So in the 1980s, there was a Russian mathematician by name Sirelson who came along and showed that if you consider two-dimensional systems, like a pair of qubits like here, and for qubits, now it turns out they are special. Because any such binary outcome measurement in a qubit, I can rewrite it in terms of the Pauli basis, right? Because when I have a two-dimensional quantum system, and if I consider the set of measurements on this two-dimensional quantum system, then I have a very special set of measurements, namely the Paulis. And the Pauli plus identity forms a basis for all operators on a two-level quantum system. So I can write down every measurement on these systems in terms of the Paulis. And then if I write down this particular form in terms of the Paulis, I can actually put an upper bound on what is the expectation value of this. And it turns out that this upper bound, I'm out of space, let me write it here. So this is for two-dimensional quantum systems. Let me just say, I'm just going to say 2 qubits, okay? It turns out that this expectation of M is actually bounded above by 2 root 2. So this particular violation that you see for this kind of a state is actually the maximal possible violation of CHSH. So for any other quantum state, so okay, a few other things which I should now clarify. So what are the ingredients that went into violating this inequality? First of all, we started by assuming that you have an entangled state. So as Sanjeev pointed out, that kind of breaks this idea that you can simply write product distributions, and you can simply take a distribution here and a distribution here and pretend like they are independent distributions and just multiply the probabilities. You cannot do that because you now have an entangled state that they are sharing, okay? The other ingredient that goes into it is this particular set of observables. So for example, if A and B were in a product state, you're not going to see 2 root 2, okay? Or if A and B had picked a set of commuting observables, you will not see a violation. So the 2 ingredients from quantum mechanics that are required to see this violation is A, an entangled state, a state which is not a product state. It need not be a Bell state, but it could be any other entangled state. And B, a set of observables which actually does not commute within each subsystem, right? Because an observable here and an observable there, of course, commutes, but basically you have picked observables PQ and RS that do not commute. If I picked all commuting observables, I would again not see a violation. And again, this particular set of observables actually gives me the maximal violation. I could have picked other observables which may not give me this degree of violation. So the point is that quantum mechanically, you can see values anywhere between 2 and 2 root 2. And for a maximally entangled state with this set of observables, you actually see the maximal violation of the Bell-CHSH inequality. Interestingly, when Bohm came up with his idea of a paradox, and Bell's paper was the first one to sort of clearly state it in so many words, right? Saying that, okay, you're assuming local realism when you're stating these paradoxes in the first place. So it turns out that if you just had sigma z and sigma x, you may still be able to explain these paradoxes using some hidden variable models. But you actually need these kind of observables, which if I now think of these, let's say, as polarization observables, then these are actually like 45-degree observables. These are like, so if I don't know if you're familiar with the block sphere picture, then this is actually a 45-degree observable between x and z, right? And they are exactly the pair of observables that don't commute along that 45-degree line, right? So, or 45 and 135, right, basically. So if I think of these as polarizations, then I'm picking, let's say, horizontal and vertical polarization, and I'm picking 45 and 135-degree polarization. So I need these additional angles between the x and z in order to actually see this violation. Okay, so yeah, just wanted to point these out. And of course, the first experimental realization of this kind of a violation was due to Alain Aspec's lab in France, and I think they did this, again, I'm not sure about the exact year, but sometime in the 1980s, exactly using polarization states of light, using a pair of entangled photons, they showed that you do indeed get something which is larger than 2, okay? Yeah. In writing down this probability distribution, this joint distribution, first I'm assuming that it is possible to simultaneously write down a joint distribution both for non-commuting observables. In this case, that gets violated by non-commuting observables. And the second is when I'm talking about these observables PR, QR, and I'm summing over these, I'm assuming that these are independent. Yeah, so this is P plus Q times R. Yeah. Correct. Yeah, exactly, yeah. So, okay, so let me, so you are right that in order to get this bound, I don't need to factorize it the way you're saying. That would be one way of getting this bound, but I don't need to do that. But I'm somehow saying that I can simultaneously measure these observables. So that is actually the sense in which, so that's why I'm saying that this assignment of values, I'm able to do simultaneously. as if it doesn't matter for B whether A measured or not. Not that they are independent necessarily, but it doesn't matter for B whether A measured or not, and it doesn't matter for A whether B measured or not. I guess one is effectively saying they are independent in a causal sense, but the point is you can simultaneously assign values to observables here and here, irrespective of whether one was measured or not, which is not true in the quantum case. When you have an entangled state, it constrains your distribution to be in a particular way. So maybe one way to see this is, suppose I did not have an entangled state and I had these binary valued observables, then all possible outcomes are possible, right? In the case of this spin state, for example, if I didn't have this entangled state, then I could get 0, 1 on one side and 0, 1 on the other side, and that's a pair of all 4 outcomes are possible. But if I now have this entangled state, then that constrains my distribution in a way that all 4 outcomes are not possible. But in doing this, I'm assuming that all 4 outcomes are possible. Does that clarify this point? Yeah, you don't need to factorize it to get this bound if I have to. But I think that you don't need to, but it is more the fact that you're simultaneously assigning values to both observables. So maybe I'll just show. So if I have this Bell state, okay, if I have this, and if I write down the possible outcomes, right, let's say just of sigma z, right, then the only possible outcomes are +1 here and -1 here, -1 here and +1 here, right? But there are 2 other outcomes also possible, which is +1, +1 and -1, -1, right? Which this state excludes. But there I'm not assuming such a thing. I'm saying that because they are causally disconnected, I'm writing a distribution over all possible outcomes. So that in a way is what this assumption does. Okay. So yeah, maybe this, I will stop here today because I don't want to start any, yeah.
Yeah, so by the way, when we say that we are able to write down, we can write down such a joint probability distribution, that essentially you are saying that there is this first assumption, the realism is there, right? That the
I'm saying that both
are
are there. See, when I write this down exactly, right, what will I do? I will take this probability distribution, I will put in the P times R here, I sum over that index. I'm basically summing over a pair of indices here to get a marginal distribution, right? I have a joint over 4, but each one is a pair, no? So when I try to write down this expectation value, I'm only summing over a pair of indices here. So I'm effectively writing down marginals, but I'm writing down all possible marginals without paying attention to A, whether they are commuting or non-commuting observables, right?
By the way, I was thinking like this realism assumption was anyway violated because initial Bell state that we had, we could look in any direction and we could actually write it like the way you showed, like you could write it as plus minus, minus plus, that way also. So it has infinite number of ways you can write it.
That
so
particular
that
antisymmetric state, yes, but realism is actually violated here because of the fact that you have non-commuting observables. See, in quantum mechanics, you cannot write down a simultaneous joint distribution for non-commuting observables. Because a precise measurement of one, or as if you have, because the distributions are basically constrained. One way to think about it is that they are constrained by an uncertainty relation using your variance. By the way, one can also write down entropic uncertainty relations. I think I was talking about this in the first lecture also. So you can use entropy as a measure and you can write down entropic uncertainty relations. So the set of probability distributions that you can write down for a pair of quantum observables is constrained if you have non-commuting observables. That is the first point. So that you can think of both X and Z as somehow simultaneous elements of reality. That is what this assumes.
is both X component and Z component.
It allows you, no? It says you can have any PQRS and you can simultaneously assign values to all of them, right? That's what this realism assumption means, that any set of observables you pick for the system are elements of reality.
But that is what is not seen in the state itself, right? That is
Yeah,
what I was telling you.
so that's why I'm saying, so locality is violated by the fact that you have an entangled state, and the realism, at least this is how I understand it, there are various interpretations of this possible, but my understanding is locality is violated because of the existence of these kind of entangled states, and the realism assumption is violated because you have non-commuting observables which cannot be considered as simultaneous elements of reality of the system.
So locality means basically this joint distribution is a priori defined. It's not influenced by the.
Exactly, yeah, it is a priori defined, and exactly. And you can write down something over this unconstrained by whether something was measured or whether, yeah, exactly.
So, by the way, this about this LN aspects measurement,
Yeah.
which was basically coincidence measurement, right?
Yeah.
So that only excludes, that basically says that the quantum mechanics is non-local essentially, at least these kind of measurements, right? It didn't say anything about the realism, right?
Like I said, the set of observables that they measured, that is where the realism aspect comes in. The realism aspect basically says, so that's exactly what I wrote down, right? I wrote down realism in terms of saying that these four quantities, it's basically saying if I measure the length, the breadth, the thickness of my tablet, I can do all of that, I can assign simultaneously values to all of that objectively, okay? But quantum mechanics says no, there are observables where you cannot assign these values simultaneously. Okay, so that is what is violated. Alain Aspec's experiment was a complete realization of the Bell CHSH test. The only thing is it was a tabletop experiment. So you can ask where is the causal disconnect and where is the space-like separation and all that. So today people talk about what are called loophole-free Bell tests. So you take these two photons as far apart as possible. People are even trying to do this with space and satellites and so on. So you take this pair of entangled photons as far as possible so that one is completely outside the causal interference zone of the other one, and then you show this violation. Because there is then still this loophole that, oh, maybe there was something when you tweaked one measurement apparatus in this system, somehow that caused something there. So you have to kind of close those loopholes completely to claim today that you have a loophole-free Bell violation.
But that still doesn't count as non-locality. I mean, if you are thinking in aspect of in a general setup of non-locality, you said the locality is violated,
Yes.
but then there might be some non-local hidden variables.
Yes. To the best of my knowledge, we still don't have something which precludes a non-local hidden variable theory. Okay. Yeah, you had a question. Okay. Yes.
So if you want to move in the reverse order, if you want to start with beta, can we construct our density?
That's a very nice question. Indeed, people do that. So they say for a particular entangled state, what is the set of Bell inequalities that it violates? Okay, so indeed you can ask this question. Things fall very nicely in place in the case of this particular scenario, which, like I said, is what we call a 2-2-2 scenario. That is two observables, two outcomes, two parties, where this is sort of the complete story, right? But then you can ask, once you go to higher dimensions, there could be entangled states, okay? I'm telling you the other way around now. I can write down an inequality which is not violated by an entangled state, okay? And that is called entanglement without non-locality. Okay, so you do not violate a Bell type inequality, but you're still entangled, but that is because you have not written down the correct set of observables which are witnessing that entanglement. So indeed one can sort of ask these questions where you fix an entangled state and ask what is the set of Bell inequalities that can violate this. Like I said, in the 2-qubit case, this completes the story. This is pretty much the only set of Bell CHSH inequalities that you can write down for which you see this violation.
In that case, we do have a particular construction. It is only that we are not able to figure out that, is it?
I didn't understand. What
Like you said that for particular constructions, we may not violate the
Yeah,
equality.
yeah.
So, in a sense,
See, the question is, this is a sort of framework I'm laying down for my physical theory. Are there states and observables which violate this? That's the only question. So even if I find one such instance of an observable and one such instance of a state which violates this, it tells me then that these assumptions are violated. Okay? So the secondary question you can ask is, okay, now I constrain my set of entangled states, then do I always see a violation with this? In the case of 2 qubits, the answer is yes. Any entangled state will see a violation of this. So today in quantum entanglement theory and foundations, people talk about non-locality as separate from entanglement. You may see some papers like that. So this is what they mean. They say that it is non-local if it violates a Bell type inequality, and they say it is entangled in the sense that the marginals are not product states and so on, the way we discussed so far. These two notions exactly coincide for this 2-qubit case very nicely. Any entangled state will show a violation beyond 2. Maximal violation is 2 root 2. So all other states are sort of nicely between this 2 and 2 root 2. But the minute you go to even 3-party situation, you can have states which are entangled but which do not violate a specific inequality. So one area of research for people is to write down all the possible set of Bell CHSH inequalities. In the 2-qubit case, there is exactly one. In higher dimensions, multi-party settings, you can write down many. And then have you exhausted that set? So if a particular state violates that entire set, can you then declare it to be entangled? So lots of such questions.
We can Schmidt decomposition only for 2A and 3, right? We cannot do the same for A, B, C.
Exactly. No, one cannot.
The argument doesn't make that sense for 3 or 4 or whatever.
So I'm going to show you a little bit about entanglement beyond 2 parties tomorrow. And there are ways in which we can talk about entanglement, but there's no unique way of talking about it, unlike in the 2-qubit case.
Maybe other 3 Bell states will also.
Yes, absolutely. They also have maximal violation. So I'll talk about the other Bell states tomorrow, and indeed they all violate, they all show maximal violation. Okay, so yeah.